2:21 in the morning. That's what time it is. Okay, so I just have a few slides that I tried to put together to come up with sort of a conceptual introduction to the grand finale, as we call it. So you have these slides in PDF form in your download folder. So the grand finale, as we've been promising all week, so combining what we started single level measurement models. We're going to have this as multivariate because we have multiple items, so 10 items in this case, combined with multi-level models, which is a univariate approach but has 2 levels of sampling where we separate each outcome into what is level 2 random intercept, level 1 residual. Those together then give us what most, in the world I live in, most of the time it would be called multi-level structural equation modeling, multi-level, multivariate measurement models. So, ta-da. All right. So it combines these 2 worlds, and the idea here is that we will have 2 different levels of our latent variables, of theta, 1 or more thetas in here. So in the context in which we're talking about here, we have clustered data. Within level 1 is the person residuals for each item. So the part of the item response that would be student to student variation. And then between level 2 would be the cluster random intercepts. So yesterday we had 1 random intercept variance because it was for 1 sum score. Guess how many we have for 10 items? How many random intercept variances would I need if I don't have 1 sum score, but I have 10 items? Don't think too hard. 10! Yes, 10. That's the key. So each item is going to be multi-leveled to begin with as a verb. Level 2 random intercept, level 1 residual, and then we put a factor on the level 2 random intercepts, and we call that the between factor, and we put a separate factor on the level 1 residuals, and that's the within factor. Conceptually, it seems straightforward. However, the decisions about what to estimate, what to turn on, what to shut off, what to constrain, that turned out to be a lot more complex than I had anticipated when I first started looking into this. I will note that this exact same set of logic and procedures would apply in longitudinal data. So for those of you who have multiple occasions or multiple days within people, then you would have random intercept would be between person mean differences, would have a between theta. Within person time to time variation would be the level 1 residual that has a within theta. Big however, though, with the last part here, that is not correct if the variables that you're working with show individual differences in change. Because to the extent that people differ systematically in their response to time or other kinds of circadian rhythms, then what you're calling between is incomplete. Between really, in this context, is just mean differences. But if you also need time slope differences that vary between people, that would have to be another factor that is represented somehow, and you could have a theta for your slopes as well. So just to put that out there, that if you have individual differences in change, that's going to be confounded with your within level residual, and to the extent that those individual differences in change have a differential relationship with some other variable, you want to make sure that those are separate. And I can send anyone who's interested in learning more about that some references and some preprints that I have. Okay. There we go. So here's a diagram that I stole from this paper because these diagrams take a very long time to make. That describes the idea. So in this example, there are 2 different factors, and there is a macro level here, which I would call level 2 between, a micro level that I would call level 1 within. So micro would be the students in our example, and macro would be the schools. There are 6 items in this example, 3 for each factor, as represented by the middle row of boxes, and each box has been partitioned into a random intercept circle here that has some variability left over, and a level 1 residual circle here that has some variability left over. So this is a multi-level CFA model where they're pretending the item responses are continuous and normally distributed. And it's hard to see on the projector, but hopefully you can see on your own screens that the idea here is that the intra-class correlation for each of these item responses, the extent to which an item response is shared across people from the same cluster, That is the limiting condition on how much information there is to go into the between level. So if you have an interclass correlation of an item that's 0.1, that means 10% of the overall item variance goes up to be part of level 2 that could have a factor predicting it, and the other 90% stays at level 1. So I think where these models start to run into trouble is for items that don't have a lot of between variance, because it's very hard then to estimate that variance and split it into how much is factor versus not the factor left over. All right, so then the question is, what do you do with the parameters? Do you make them equal across levels, or do you make them unequal? Yes?
So what ICCs do I have a problem? Is 10% not enough? Is 5%?
I don't know that there's a ready answer, and that's why I have quotes around what enough is, because I think it depends on your overall sample size. I think it depends on the strength of the factor that would underlie the item responses. What people tend to do, and what we'll see in our example, is this idea of leftover variance at level 2 for the random intercept often gets shut off, fixed to 0. So then what they're saying is that the item random intercept is entirely predicted by the factor. Idea of that face. I'm not so sure about that. Well, it's an empirical question, the extent to which that model is not worse than letting them be something else. But I think there are circumstances in which you would want to do that and circumstances in which you would not. It depends on the nature of the theta that you're trying to estimate.
And what are examples for?
Oh, I'm so glad you asked. That's coming up. So give me 30 seconds and I'll get there. So one implication of the fact that we have a measurement model operating on 2 orthogonal levels simultaneously is that all of the processes that we would normally go through to evaluate the quality of our measurement model, we got to do twice. So the idea, does it fit? Are 2 factors enough? Do we have any remaining item-to-item correlations that the factors are not adequately representing? How reliable are our factors? If you had to guess, if you only have 3 items going into each of these factors, do you think these are going to have strong reliability? I wouldn't think so. Unless those are super, super good items, 3 is enough to make the model identified, the factor identified, I should say, but it may not be enough to get an adequate representation of the factor. So it depends on, I think, what you're trying to do. Are you trying to sell thetas in which you want to have reliability as maximum as possible to make an individual distinction? Or are you only interested in this to examine a relationship of how the factor predicts some other things? Maybe you can live with less reliability in that case, but if you're making decisions that change people's individual lives, you want as more reliability than what 3 items could probably provide. Validity, too. So a factor, as I'm fond of saying in my SEM class, is just the covariance around items with a circle drawn around it, and you gave it a name. There's no way to say that my name is any more correct than your name, because we don't know why these items have something in common. We know that they do. So the process of saying, hey, is this cognition, or is this just working memory, or is this, this, or just this some set of this? That is validity, right? And that usually relies on some kind of external evidence. Well, this factor is related to this other thing, but not as much to this thing, so that means I think my label is right. All of that type of investigative analysis would have to go on each level separately. And so in this literature, you'll see suggestions as to how you should best evaluate fit when fit is happening on 2 different levels at the same time. Usually it's some version of try to saturate one level and just focus on the other, and then switch it, saturate this level and focus on that one. Because otherwise you end up with some sort of blend where the model might look like it fits, but it only fits at level 1, and level 2 isn't really represented as well, but you don't have as much information about that. Okay. So first question then, do I have to do this? Can I just do a single level IRT model? Isn't that hard enough? Yes, it is hard enough. So this approach of ignoring clustering has names, and depending on who you're reading, it might be called an individual analysis or disaggregated, which to me is an odd one. And literature that has examined these issues via simulation has found that so long as you're in a sampling context in which there's way more level 1 observations than level 2, which is usually the case, exceptions to that might be dyadic data or family data where you have very few family members per cluster, the estimates are probably not going to be that far off because the level 1 model is going to have most of the information, just as we saw with the smushed effect. The smush slope looked a lot more like the within slope, but that just means the level 2 model is going to have misspecification in it. Standard errors for your measurement model parameters are going to be too small because you're ignoring clustering. You don't have as many independent level 1 people as you think you do because they have things in common. So your effective sample size is not your actual sample size. And then one that I thought was sort of surprising, model fit looks too bad. You would come to the conclusion that your model doesn't fit if you ignore clustering, even if it does. So to me, that might be the biggest argument, is that you're going to try to troubleshoot model misfit in a way that is artifactual because it's not the model's fault, it's the sampling design interacting with the model that's causing the problem. So these are some valid reasons why you would go to the trouble to fit the grand finale model. It's relatively straightforward in application. So I use M+ to teach SEM, and they have plenty of multi-level measurement model examples, and it looks very simple, and it estimates in seconds. Of course, their data are perfectly behaved, fake data, so that always helps. But then in terms of how do you actually talk about a between theta and a within theta? Like if you're going to write your discussion section and say what you found, how do the choices that you make in terms of model specification influence your interpretation of what these latent factors contain?
Can I ask a question?
Uh-oh.
Sorry, not to belabor a point. So let's think here. You're putting a random intercept on every item with a person level factor involved in it, right? Like on the item itself, like within the level 1 factor.
Yes, level 1.
Okay.
Yes.
So my terminology is very different than yours. Let's say I'm part of a testing program, and I'm really concerned about differential item functioning, where I did a measurement and variance, and I found a set of items that differed on their intercept across, let's say, groups of people or schools or whatever, and I removed those items because I don't want to have any implications of bias. Would I then shut off the ICC if that's the grouping variable? Or would you say that no, that's
Not necessarily.
Not necessarily. So what is the relationship between a random intercept on an item and measurement invariance? Are you saying that there is no measurement, you have measurement non-invariance on an item across groups?
Give me 2 slides, and
Okay.
I will answer that question.
Okay, I was going to say. Because that seems to be like counter to what we want in measurement, right? We don't want variation across groups on intercepts. And you're saying, oh, but we can get better model fit if it exists.
You could, yes.
Okay. Is that a good thing or a bad thing?
Not necessarily.
So-
It depends on intent, I would say. Okay, how are we doing? 2 thumbs. Okay. 1 thumb. All right, I'll take 1. That's fine. As long as it's not 2 thumbs down, right? That's sort of the worst we can do. Question?
So I follow that maybe there is another clustering factor that I don't consider, and then if I consider it, my model would fit better. But to consider a cluster in a multi-level model, it has to have some representation of the cluster, or enough. Let's say I only have 3 different groups in that cluster, then it's not enough to consider, right?
No, that would be a situation in which if you only have if it's say students in schools, and then the schools are drawn from 3 districts or 3 states, something like that, I would treat state as a fixed effect. Just put dummy codes in the model to control for differences, probably at the latent trait level, potentially at the item level, and just let it be saturated that way. Because you would not want to add another source of random variation for another type of clustering unless you had the sample size with which to actually estimate the variability in that dimension.
And could I also control for that in the multi-level complementary factor analysis?
Sure. Yep. It'd just be a box in your model. Paths. Okay. Yeah. All right. So word salad. Are you familiar with this term? This is my summary of the different places I tried to read about people talking about these models, and they don't agree on the terms, but there are some common threads. And some of the decisions that you would make about how to set up your model, what to fix equal across levels, what to not fix equal across levels, depends on the thing that you're measuring and whether the group is the purpose or it's sort of beside the point. So in one type of cluster level construct, the cluster is what is being described. So if you have individuals in a workshop nested in instructors, hypothetically speaking, and you're given a survey at the end of this workshop that describes your impressions of us and how this class went, right? You have your own opinions, but you're all rating the same target. There, the purpose of the measurement really is to measure the cluster. You just can't do it directly. You all are the indicators. Then in that case, really it's level 2 theta where the focus would be in terms of how you would talk about this. And any variability that's left over within a cluster either represents unreliability from one perspective or disagreement from another. Maybe there are some workshops in which the participants are more homogeneous in their evaluation, and there are others where the participants disagree. Another plug to types of models that can address that, location scale versions of these models allow you potentially to have a different level 1 residual variance across clusters that you can then predict the amount of as another linear model. So it is possible to relax the assumption that all clusters are equally homogeneous and to determine why that might be. And in these sorts of situations, predicting the extent of agreement of people within an organization might be something that's of interest. In our context, and in a lot of contexts, the clustering is sort of accidental. The items that the people are rating are meant to describe their math ability, or their personality, or their tendencies, and the extent to which people from the same environment share similar tendencies is just sort of an accident. That's a different type of situation in terms of, do you really care about the between level theta, or is it just something that you have to control for in order to get a decent estimate of the within level? So in this case, within level 1 is the target. Between level 2 is just sort of, yeah, it's in my model to make sure that I didn't mess anything up. And I just have a little bit more terminology here. Multi-level IRT is what it would be called if the items are either binary, ordinal, or nominal. I think those are the main categories. And I have CFA or SEM for the multi-level variant if it's what I call continue-ish, because item responses are never continuous, but we can pretend like they're continuous enough to be able to do something with.
And the term multi-level IRT, these models are a bit different from some of the original multi-level IRT papers that came out. I'm thinking Jean-Paul Fox and Kees Glass, like 2002.
Not necessarily.
Well,
once you put the constraints on.
When the people shut off the random intercept variance, that's the model that you get from that back. But the evolution of where this came from with thinking of, I've got random intercepts for item, wasn't thought of in that manuscript or that paper. So I think that's why this sort of is a little bit of a divergent path, starting with the multi-level, I would say, less so than the IRT part. So.
Do you know what he's talking about? The idea of like a 3-level model of items are nested in people or nested in clusters. Have you seen that before? So it turns out that's the same thing as this. If you fix all of the loadings everywhere to 1, because it's a Roche model, and because 1 is the only loading that you have, it's equal across levels, and you would shut off or constrain to 0 the leftover random intercept variances here. Then it reduces to items nested in people, nested in clusters, and I believe that's one of your models?
Yeah, one of them.
That's one of them. He's got one of those. So, as a highly constrained version of this, the nice part about that model is that it does simplify down to something that univariate multi-level software can do. So that would just be treated as a standard 3-level model in Elmer or Mixed or any of those types of packages. Okay. Sure. Go back to word salad here.
Maybe I missed the point, or maybe we are not there yet, but what do you get from the level SEM in terms of of person parameters. Is it the same same trait for level 1 and level 2, and then we make inference about that one specific factor trait in different levels, or is it just more from a substantive point I was looking at?
So the question is, do we assume that it's the same trait and we have the between part and the within part, or are they different things? Is that right?
Yeah.
It depends on your model. That's actually next. So one way that people have talked about the logic by which you constrain things across levels or not, with potentially that goal in mind of making it the same thing, is related to measurement and variance. And when I first started reading this, my brain broke, because it's like, what? How is this related to that? But if you think about, say, a traditional measurement and variance analysis, or what it's known in IRT as differential item functioning, you might have a comparison of item parameters across two groups where people are nested in those two groups, and you test whether the loadings are the same across groups, whether the thresholds, intercepts, or difficulties are the same across groups, whichever version you're in, and potentially whether the residual variances are different across groups if you had that as a model parameter. So if you think about the clusters as many, many groups, then the logic stays the same. So the literature has differentiated both the differential item functioning side with respect to IRT, where you might say that there is measurement non-invariance of a uniform variety if only the intercepts or thresholds differ across clusters. If the loadings differ as well, then they would call that non-uniform diff. In the CFA version of measurement invariance, or factorial invariance as it is called, you would say that you have at least configural invariance if it's the same type of factor structure at both levels. So like in the picture that we just had. It would be considered weak if you have the same factor loadings at level 1 within and level 2 between. And this is what you would need to be able to say, no, I have a theta, and I've differentiated its between level 2 cluster part and its within level 1 person part. The constraints have to be there on the loadings to be able to say that it's the same factor and that you have basically done a multi-level analysis on the factor itself. Otherwise, you can't say that. Strong then would add a further constraint of shutting off the leftover random intercept variances. So at level 2, the data that you're working with that's being factor analyzed are the 10 random intercepts, one for each item. Then you have your between level theta that's predicting them. What strong invariance would say is that after controlling for between level theta, there is no more variability in your random intercepts. Theta has it all. Now that seems like a very strong statement, but from an invariance perspective, what you're saying is that the expected item response only depends on the trait. It does not further depend on which cluster you're in. Because if you leave the leftover random intercept variances estimated, you are allowing differences in the expected item response based on cluster. That's a violation of scalar invariance. So if you want to be able to say that there is no extra impact of cluster beyond the trait, you'd want to shut them off. But if the model doesn't fit, if the data don't support that, then you would have to say, no, actually your success of answering, your probability of answering this item right depends not only on your trait and your school's trait, but on something else that's cluster specific and we don't know what that is. So that's measurement non-invariance from a classical perspective. Do you want to add anything?
So it's theta the same.
It is, if you can at least constrain the loadings, is where we've landed on this. If not, you really can't talk about it as a between theta and a within theta. They're just two separate things.
And then the within theta, what does it represent if the loadings are constrained?
I would say that that represents within cluster differences in the latent trait. So
a person's deviation from
Yeah.
their school mean is what that looks like now.
So in the
So-
same, good.
No, that's basically what I was going to say. If you can make the argument, and it's clear when the loadings are the same, I think reasonable people may disagree if the loadings are different. But, that being said, if the loadings are the same, then it becomes very clear that the within theta and is just a deviation from the school mean or the cluster mean, the level 2 mean theta itself. So if you were to go and compare this with just a single level IRT model, it wouldn't look the same until you added back the cluster mean to it.
Yeah, so then it's like you have one overall trait and you've partitioned its variance into level 2 and level 1 in the same way that we did that with the sum score. So equal loadings would allow you to say that with, I think, greater confidence, particularly if you can shut off the random intercept variance that's left over. So arguments for and against. Some folks I've read say you should always try to constrain the loadings equal. It helps convergence even in situations in which the simulated data were not equal. There's an article, I know, here's the article. You can read it yourself and come to your own conclusion. There's also then shared identification across levels. So the linkage of loadings equal across levels then means that you only need to estimate the variability of, you can either constrain one loading to 1 and estimate the variance of both traits, or you would constrain all the loadings equal, estimate them all, constrain the variance of within level theta to 1, and let the variance of between level theta be estimated. But it's a shared identification across levels in the same way that you have in measurement and variance once you put constraints across groups on the loadings and intercepts.
You have a question?
Yes.
Just to be clear, if we equal the loadings, we could assume we have a common trait between the different schools. And if it's not the case, could we run any kind of cluster cluster procedure, maybe to find out groups of schools with different traits?
Well, so there's a school trait and there's a student trait. And if the loadings would be unequal between the school level and the student level in this example. And so the question would be not that the school traits are unequal, right? But that whether the school trait represents the average of the student trait within the school. I think that's the question. And I think it sounds like the consensus is the answer is no. If the school level loadings are unequal to the student level loadings. So I think we'll be able to talk again about this once we have a little bit more of the notation and the syntax as well too, because we'll be able to see what is constrained versus what's not. Right now, like there's so many parameters to this, like pointing at which is which. I keep losing track myself, so it's very difficult. Yes.
This is really interesting because we are we have longitudinal data, so people, and then the between is considered to be the between people differences. But for I'm thinking now that if you average the single measurements of a person, it's considered to be their trait.
Mm-hmm.
Mm-hmm.
And can I also get this information whether this is true only by looking at the loadings or no?
I'm not sure I follow. Keep talking.
No, I'm not sure. Can I see somehow in the model, or do I have to assess that differently? Whether it's true that using or looking at the loadings, I don't think that you get the information by looking at the loadings whether this assumption is true.
It would be the latent trait estimate that would be like your average. So if you the level 2 in this case, latent trait would be the version of your averaged across time, I believe. The person mean, you're saying, right?
Mm-hmm.
Does that? I don't know if I'm answering your question, but the loadings themselves would help the model figure out what that value happened to be. So.
It is the case that in longitudinal data, like daily diary kinds of data, that people frequently would say, well, your average across occasions is your trait value. Like this is the part that's constant and this is the part that's fluctuating. But it's an open question as to whether if you ask someone every day of the week, how grumpy do you feel today, versus how grumpy would you say you tend to be overall, like whether those answers would match. I don't think you're guaranteed to know that, and there's a lot of reasons why they wouldn't match, but those are two very different ways, I think, of getting what a person's standing is relative to other people. Because it could be just that they had a really bad week, the week that they completed your survey, and they're not normally that grumpy, or it could be that they're delusional, or they want to present as if they're not grumpy when you ask them directly. So that's one other nuance to keep in mind.
We could kind of solve this with having a lot of people. right?
I don't think so. I think that you would end up potentially with different answers, and which is more correct would be it's a more of a measurement philosophical issue than a modeling one. There's not an easy answer. Yes?
But I don't think it would necessarily be a problem, because in our multi-level analysis we just want to have, like, we just want to put into the model that there's also some kind of person and trait variance, but we're not interested in saying, we're not assuming that just because we measured across days, this is their trait level, because usually we have then our separate analysis on within, or hypothesis on within and between level. If we have something that's about traits, then we measure it in the beginning of the diary study, right? And then it's not measured over time. So I think here it's just the idea of whether the parts of answering every day, whether those factor loadings are then also the same. Well, there I'm not sure how to say correctly.
Yeah, I think I see what you're saying.
The idea was correct, but just that in the diary studies we don't treat it equally. Like, we don't think about, okay, what we measure across the day should also be equal to what we would measure if we just ask them once about their general trait characteristics. It's just splitting up the variation, right?
Yeah, if you're not interested in talking about why people differ from each other and any of that variability, then you can absolutely ignore what I'm saying. But if you want to try and interpret level 2, I think that's something to keep in mind. Would you get a different answer if you ask someone, what do you tend to do, versus try to extrapolate that answer based on what they said every day? And if you ask it in baseline and you collect the daily answers, then at least you've observed it both ways, and you can potentially try to see to the extent to which there are differences as a function of how trait variance is measured.
Yeah, I mean, I guess it's taking us a bit away from that, but I kind of have the same issue, and I was wondering if I have a trait measure, like you said, and then also, but I could also calculate the mean tendency of the states, right? But including both would be kind of overkill, right? Because they would probably also be highly correlated.
Empirical question.
Yeah.
Yes, ideally, yes, people would be good. Like, it would be internally consistent, like the average of their days would match what they say they tend to do.
Yeah.
But I don't think that's a guarantee.
Right. So you mean I should figure out like how strongly they are correlated and then decide whether I could include both? Because if what we discussed earlier, right? If I person-centered state things, I kind of lose the overall tendency of the person, right?
Yes, yeah, but that's sort of the point, is that you're trying to not talk about between-person differences. You're only focusing on within-person processes.
Yeah, but if I would still be interested to have that include anyways at a level 2, then yeah, I would need to figure out whether I should include both or not.
Or how best to. So in theory, if you could get a third way to do it, maybe ask someone else, like, how grumpy does this person tend to be? Then you've got 3, then you've got a latent factor. So
yeah, okay. That's a whole new project.
It is a whole new thing, but that's just another idea.
All right, thank you.
Okay. So what we were talking about, to try and put the picture up here, is whether or not these loadings need to be equal to these loadings. They do if you want to be able to say that what I have is a trait, and I have the between part of it and the within part of it, and I can put it back together again as a whole that makes sense. If the data don't support that model and you end up with different loadings at the between level than the within level, then you can't say that it's 2 halves of the same trait. It's just 2 different things. And in that situation where the between loadings and the within loadings are different, and so the traits are conceptually different, then it would make sense to allow these random intercept leftover variances to exist. Because otherwise what you're saying is that your trait measurement at the between level is perfect. That everything is due to the trait and there's nothing left. And I think if all you're basing that on is level 2, that's a very strong, unrealistic assumption. If you have the constraints across levels, then maybe it's a more reasonable thing to do. All right, I think I'm about done. Yeah. So one thing to keep in mind is that a lot of this literature is using the CFA case because it makes everything a lot easier. In the CFA case, you have that residual at the end of your measurement model equation, which means that you can do the partitioning of variance into within residual, that's an observed thing, and between random intercept, that's an observed thing. And that ability to have a residual variance at level 1 as an estimated parameter in the CFA case then allows you to do things like saturate level 1, Well, just let all the residuals be correlated. That way you can focus on the between model. And then you could let all the random intercepts just be correlated so you can focus on the within model. That's the ideal way to test fit, to make sure that it's level specific and that the information from level 1 doesn't swamp the information from level 2. You can also shut things off. So one of the questions is, is there enough clustering for me to worry about? The empirical way to test that would be to shut off level 2. Right? To constrain all the random intercept variances to 0 and then say there's nothing up here to model. So in the IRT world, you lose some of this flexibility simply because at level 1 there is no leftover residual variance that you can then do things to aid you in the process of diagnosing misfit. The other thing, intercepts in these measurement models become unit specific. So they're not really the mean, I guess the expected response. They are the expected response conditional on a between level trait of 0, which is a slight distinction, but one that can be important. And then we were arguing back and forth for at least a week or so on whether or not the level 2 factor loading should be between or contextual. Because we're not really doing the equivalent of cluster mean centering. The factor is predicting the original level 1 variable, not just the within part. So there's some ambiguity into what we get back. And where we landed, where he decided that we landed, and I agreed with him, is that because the within level theta and the between level theta are uncorrelated, that structure maps onto the cluster mean centering or latent centering version where there is a clean demarcation of within and between, and it's not within and contextual. So that is our best guess as to what you would interpret these factor loadings to be. I would also say that in general, a strategy that you can use to figure out if your level 2 parameters are between, meaning not controlling for level 1, or contextual, meaning after controlling for level 1, is to change the level 1 model. If you have a slope at level 1, change it to a covariance. If the level 2 parameter that corresponds to that same relationship changes, it's got to be contextual, because it's controlling for in one case and not if it's a covariance instead. So that's a general strategy that you can use in these models to make sure that you know what's happening at level 2. And with that, we got the grand finale set of 8 models, and maybe there's a 9th and a 10th by now?
A 9th. Yeah, a 9th. Well, just as a heads up, we haven't had a chance in the evening to update the files or the videos, but we plan to do that. If we have internet on the plane tomorrow, we got a 9-hour flight, so hopefully we'll do that. Hopefully we'll do that on the plane, but we will email everybody at some point within the next 4 or 5 days with the updated links, with all the materials, and so the archive that we have promised you will be there. It's just the evenings have been a little bit later than we expected to be able to do this. So. Well,
to be fair, he's still running models in the evening after we've already been talking with people for 12 hours, right? So please forgive us for not having worked overnight to make sure that everything is in your download package.
But Stan does. Stan works overnight.
Yeah, Stan works overnight. He wakes up in the morning. Is it done yet? I need some coffee. So yes, that's the nice thing about the internet, is we can update this stuff and we can send you a link and you can have it all for your future reference. But these are the models that we're going to look through. They're sort of like ascending in complexity. So, you get one simple thing working, then add a layer, make sure that works, add another layer, make sure that works. And what differentiates these models is highlighted in red font here.
And let's be clear, none of these are really simple, but...
Simple, like simpler, right? Like within grand finale centered, number 1 is simplest. Within grand finale centered, 8 is the worst, and now there's 9 forthcoming. But we also have equations that go with these, because as he said on the first day, a path diagram is not a model. It's just a way to try and describe conceptually what a model is doing.
And honestly, I think in equations, and when this research was coming out, people would show me these path diagrams. Like, I don't know what you're doing here. Show me the equation. They're like, well, I don't know how to make the equation. Like, how do you know what you're doing? Yeah. Is it my turn now?
I think so. Can you pull it? You can pull up the equations.
Yeah, I can do that. Let's put this in. Hello, everybody. Apologize for being late this morning.
He hates on my mouse.
There's a beautiful trackpad. The human factors of making a Mac is just impressive. Never mind. All right, let's forget that. I want to start with the equations. So the first, actually, let me start with the words first. The first model is a model where we take the 10 observed items, right, that we used to make the sum score from. Now remember, our goal in this analysis is to eventually create a school-level version of ability of math, and then to predict that school-level ability of math with a school-level free and reduced lunch. Technically, we're also going to predict a student-level ability of math with the student-level free and reduced lunch. So this is a analogous set of we're building toward what we wanted at the end of yesterday, where we described some 80% of variance in school ability based on free and reduced lunch. But because the sum score was not perfectly reliable, we were trying to do this in a latent variable context or a multi-level context.
And because the 1PL didn't fit as well as the 2PL, which means the sum score is not an adequate representation of the trait anyway.
All of that. So we're going to start, though, taking a step back. We have these 10 items. Normally, when I see 10 items, some type of questionnaire items, the first thing I think about is a latent variable. But let's not do that. Let's say, wait, let's look at our nesting structure. We have students nested in school. Each of them gave us 10 pieces of data. Instead of doing the latent variable approach, let's switch over and do the multi-level approach. Let's go take a look at, first, let's go take a look and see if there's any random intercept variance. Let's put a random intercept per item on each of the 10, just to see if there's any random intercept variance. Right? So what this implies is effectively, if you remember yesterday, we started with the free and reduced lunch, the 0-1 variable, and we tested an empty model for it, and then an empty model with a random intercept. So essentially that latter one, empty model with a random intercept, for all 10 items, all at once. Okay? What are you laughing at?
On the plane on the way over, I watched the movie Everything, Everywhere, All at Once. That's this.
So this model, this is model 01 Stan. Do you want to talk?
Yeah, I just wanted to give a disclaimer. So we tried to come up with equations for this, and it was quite challenging to find a notation scheme that would work, and we landed on something that we think works. And because the working memory to figure out what this means is really a lot, I have this whole dictionary of what all the stuff means that are on the equations that follow. So if you're like, what? This is your page to come back to as to what each of these terms is supposed to mean.
So I have to admit, I've never really, I come at things from the more psychometric perspective. So yes, I'm a fan of multi-level models, but it never dawned on me to be like, hey, let's go and put random intercepts on all these items that are correlated, right? I don't know if you've ever done that before, but I was, why would we do that? But now I'm like, oh, I totally get it now. So this model, we have Y, which is our math item for a person, in this case, cluster and item, right? So there'll be 10 of them. The logit that Y, the probability that Y is 1 is equal to our placeholder intercept, which is equal to some, what I will call fixed intercept, but we understand in days that nothing is fixed, and some random intercept itself. And here's the kicker, right? Each item will have a different fixed intercept, right? Because each item has a different effective number of students who are answering it correctly. Although, again, this is not back translated. This is you can't get the proportion, the marginal proportion of people answering the item correctly from mu, putting it on the probability scale. But because there's variation in that, each item gets its own intercept. Each school gets its own random intercept per item. So you think of what we're estimating here. There'll be, for 10 schools, for 62 schools, 10 item level random intercepts. So it's a 62 by 10 level, like a number that we're trying to estimate. Right? So that's 620 random intercepts that we're trying to estimate. Okay? And because each school now has 10 random intercepts, those random intercepts we assume follow a multivariate normal distribution. That multivariate normal has 10 dimensions. Like every multivariate normal for random intercepts, we have a zero mean. However, we're going to have a 10 by 10 covariance matrix of the random intercepts that we also have to estimate. Right? Because yesterday when we added the random slopes, at the very end, I just threw down the Koleski, and you were like, oh. But it was a precursor to this, right? Because now we have to estimate this covariance matrix in stands. So you'll see that code again. I won't dwell too much on the Koleski, and if ever you want to try to estimate it yourself, go back to my syntax, or if you'd like, send me an email. I'd be happy to help out wherever I can.
The stand code is all in their packet, right?
Yes, that's correct. Any questions on the model so far, or the premise of what we're doing? Okay. I will, let's go here. Quick action. Go to VS Code. So this is 03 model 01 that we'll be running, which is, let me clear the console out. So let me describe the syntax for you just a bit. Here, let's go to the model. Always start with the model for me. Here we're going to use Bernoulli logit again, but now you'll see we have a loop of person. We loop over people and we loop over items. So instead of doing a shortcut anywhere, we're going to have our person item. Y is our data set that we use for IRT. But remember, items come first because of Stan's silly array being row major. So items and then persons. All right. This is a Bernoulli logit, just like we've done before. This gamma, although it's mu in the notation, gamma, I did not update all of our slides after we made the notation. Should have worked differently, but this is our quote-unquote fixed intercept per item, so there's 10 of those. And then we have our item random intercept for school, and now here we have to denote which school we have. So each person is within a school, that's our school ID, this is our person ID, and then which item that applies to. Okay, so far so good. So what are the parameters? We have gamma. Gamma is just like an item intercept. So it follows a multivariate normal distribution. We give it a prior. We don't usually just have a diagonal covariance matrix itself. We have item random intercept. Now this one gets much more interesting. The item random intercept, this is where we use that multi-normal Koleski. So we have the Koleski decomposition. So we have a vector. This should always be 0. So to do that hard-coded, I just left a vector in R just to make it a set of zeros. So we don't ever input it. We don't ever want to mistakenly put in a mean value for our random intercepts, because that would change a whole lot of things. And then the prior covariance matrix for gamma itself, this thing, that's weird. No, that's the gamma, sorry, this one. Sorry. All right, item random intercept covariance matrix. This is the lower triangle of the covariance matrix that was given by the Koleski decomposition, right? And so again, what do we need for that? We need a correlation matrix, which is also lower triangle, and a set of standard deviations. So each item has its standard deviations. Each random intercept has a standard deviation. Again, I've used log normal for the standard deviations, where we import the prior mean and we import the prior standard deviation. So in this case, there'll be 10 standard deviations, so there's 10 means and 10 prior standard deviation values. The correlation matrix, again, we're using the LKJ prior, which you may not appreciate now, but let me tell you from my background, this is amazing. I wish they had it in 2002. And that thing will have a prior hyperparameter that's almost always 1 unless we have estimation difficulty. And then we put the two together into the covariance matrix by using a diagonal premultiplication of the standard deviations with the lower triangle. So to just stay on the parameter side just a moment, what we will want to do is to not output the lower triangle of the Cholesky, because that is impossible to interpret. So here we are going to put it back together into regular matrix itself. So the correlation matrix is the lower triangle multiplied by the upper triangle, which is a function in stand, multiply lower tri self transpose, which is a long name. That looks like a name I would give it. So
It does.
very long names of the correlation that we have every step. The covariance matrix we reform again, and then do the same thing, multiply lower tri self transpose of itself. So these are really what we're interested in. What's the correlation amongst random intercepts, and what's the covariance of random intercepts across schools? So that is what the key in this model is. And then later on, I have model fit and LOO WAIC information if you wanted to go and calculate that as well. So for model comparison. Okay, any questions? That's just parameters. Any questions? If I go through this a lot, we're going to add to it. So a lot of the things will stay the same, and I'll be able to talk through those a little bit more quickly. In terms of data, actually, let's just see parameters. The item random intercepts themselves, again, it makes us make an array of vectors. These are real numbers, right? Floating point numbers that take any value on the number line. So that item random intercept will be again, 62 school by 10 item matrix. An array of vectors is simply a matrix, but it's Stan. We have our item fixed intercepts. We have our lower triangular correlation matrix, and that's a special type of variable in Stan, which is the Cholesky factor correlation. So it anticipates it just being a lower triangle. And then finally, a vector for our item standard deviations. So that's parameters. And then finally, in data, we need the number of people, number of schools, number of items. So that's a little bit different from the IRT model, and now we're sort of combining multi-level with IRT. For the items, and this is where, when you talk about wide data versus long data, our item data is actually wide, right? So we're going to import a matrix of data that's, in this case, 10 items by 3,100 people, right? So it's our data matrix that we've been importing throughout the week. We need a prior mean vector for the gammas, the fixed intercepts. We need a prior covariance matrix for those as well. That's going to be diagonal. And then here's where we start to see things that are a little bit like in the long format. The school number, the school ID for each person is an array that's an integer, because we have to use it as an index. So it's a long piece of data. So what we're going to end up getting to when we add free and reduced lunch is it's going to look like that too. It's going to be a long piece of data. So we have wide and long being put into Stan. So you don't have to have one format. You can do whatever's easiest. And so for me, this was just the most accessible. Anyway, any questions so far? All right. And then finally, item random intercept standard deviation mean. This is for the standard deviation of the item random intercepts. So there'll be 10 of those, and our LKJ prior hyperparameter. So going to the code. Excuse the scroll. Let me get this set up real quick. I am not going to even try to estimate this in person, otherwise it will be the end of the day, so we'll just forget that. Let's grab the results. And here, I'm going to look at the key parameters of gamma, random intercept standard deviation, and item intercept correlation to see convergence. Lo and behold, it converged, sort of. That's pretty good. And let's take a look at what we have. Here is a lot of correlations. All right, let's start with gamma, shall we? These are our item fixed our fixed effects, even though things fixed in days. Again, this follows the same trend. Remember, the first items were the harder items, and the first 5 were harder, and the second ones were easier. Then, forget the L part. These are our standard deviations. So this is, if we wanted a sense of, if we wanted to calculate ICCs per item, we take this number squared and divide it by this number squared plus pi squared over 3, right? Because of that crazy ICC and logit models. But what this tells us is there's quite a bit of variation in item random intercepts across cluster, because those things, these values, this set of SD right here from line 111 through line 120, none of these are especially close to 0. Right? So we have some variation across clusters in each of the item intercepts. So then we can look at correlations. I'm not going to, there's 45 correlations, right? And actually this spits out like all the permutations, if I'm not mistaken. Oh, no, actually it doesn't. So just the 45. I'm not really interested in looking through all those, but if you take a look broadly at the numbers, they range just in what's on the screen right now. I think the lowest is somewhere around 0.55, and the highest goes up to, I don't know, 0.8, 0.82, 0.83. So what we're looking at here is items, school level random intercepts are correlated across the items, is what you would expect. Pretty highly. What do you think of this?
I was just going to make a point. These are Pearson correlations because random intercepts are continuous variables.
Yes. Yes. Well,
So at level 2, everything is like C of
I wouldn't call them Pearson.
Okay.
They're maximum likelihood estimates of a multivariate normal distribution's correlation.
Okay. They're continuous variables. Is
They're
what
continuous variables.
That's what I was going.
Yes, these are continuous variables. So these are correlations of the random intercept values. And I haven't shown those to you, but if you wanted to see what I'm talking about with random intercepts, right here, if I did, quote, nope, that's not it. There we go. These are the actual random intercepts themselves. So these are each, this is, the school is the first index, the second index is the item. So this is like the random intercept for each school for item 10 and so forth. That's what's being correlated that gives you those numbers, those correlation values. And those are on logits scale, right? So this the correlation of logits is what we're getting here. How's it going? All right? No? Any questions? Well, let's go in the back and then I'll come to you. Yes.
I'm confused about those correlations between the random items for each school and what exactly is that telling us, or you just estimate to have it, or
Well, so what it's telling us is a school's deviation from the overall average for the item. That happens to be correlated across each of the items themselves. So you can think of a school mean, a school average. So the school averages, or how if a school is high on one, if a school is above average on one item, it tends to be above average on the others. So this is like a latent variable correlation. Like if a person's high on one trait, this is high on another, but this is for schools, which is the weird thing about it. We're measuring schools with this.
So these are not random items. Items are fixed in the sense that we have separate parameters for 1 and 2 and 3 and 4. So there is no random variance in item difficulty here. Just to make that point. This is not a cross model in that regard.
Yeah, these are all schools. Yeah.
Yes. Yes.
Did that answer your question? Okay. The question from the middle, your question, sir.
Yeah, it was also the substantive.
Yeah, what does it mean? I mean, I don't ever think about that. When we go and look at psychometric data from a cluster, this is starting to build the cluster idea of us using level 1 units to measure the level 2 trait itself, which is just, like, to me, to get my head around that has taken a few years. Honestly, I'm not deep into the literature in it, so that's part of why. But when I think about it, I'm like, that's weird. But this is what it is. I mean, we now have, if you think about what we're doing in a Bayes sense, these random intercepts right here, these values you see, are now a continuous variable representing whether or not a school is above or below the overall average for that item. So school 62, a 0.604 means they're a little bit higher than the average school on item 10. And if you go and look at item 10's correlation with the other items, you'll see there is a positive correlation, meaning we would expect if we go and look at item 6 or school 62, I imagine we'll see positive values for each of those. In fact, I can do that real quick. This is school 62's random intercepts. Right? So now all of these are above average. Right? So that would indicate part of what we're seeing in that positive correlation, that if a school's mean is better than the average school on one item, they tend to be more better than the average school on each of them. Do you have anything to add, Lisa?
I was just going to say exactly that.
Does that make sense? It's weird, right? Like, we're not, forget the people, who cares about them? You're just part of the machine, you're part of the school, right? We want to know the school. No. So here's the catch on it, right? Where we're going, like if you see a bunch of continuous numbers and you're a psychometric person, first thing you think is, hey, I could factor analyze each of these, right? This is what's going to be the input for our school level factor, right? We're going to put a factor model on these things. And that's where the multi-level IRT comes from, or the multi-level model comes from. But they're continuous variables, not discrete now, right? Even though they don't exist. But we've seen this in other places before. If you fit a 5-dimensional factor analysis, let's say you have big 5 personality data, right? Someone might come along and say, wait, those 5 factors, is there a higher order trait that they represent? So that's effectively that, right? We have 5 factor scores for each person, and we're going to say there's one factor that causes the factor scores. Here we're going to say there's one factor that causes or that implicates why a school has these levels of random intercept. So, which is, again, once you get to this part, like for me, this was the key that unlocked the rest of it. Like, where are you doing it? Because Lisa showed me the model at the end, and I'm coming from, again, like the Jean-Paul Fox world where I had like the older paper that was really instrumental in some of the estimation things I've done. Anyway, and it didn't have these. I'm like, where are those coming from? It's like, oh, you have to have a random intercept for item. Oh, that's it. After, a few hours of you convincing me it was right. So, questions on any of this? Weird? Acceptably weird, I hope? I don't know. But, okay. So that's model 01. This is not the multi-level model that we're after. So now, we are going to go and say, wait a minute, we forgot to add in the person trait, right?
Yeah.
So,
New things in red.
oh wait, yeah, actually we should probably control for the effect of person too, because people matter, right? So we're going to add a person theta. And again, to build this in a sequential way that's a little bit easier, because we keep waiting for it to break. I think that's what you kept telling me. So, and it will break, I can tell you. We're going to estimate a person theta where the person theta does not have a slope or a factor loading to it first. So this would be like if we had a fixed value for an intercept here, this would be a Roche model or a one parameter model. But what we're going to do then is take our person trait, give it a 0 mean, it has a residual value, that residual value has a variance. Back in the IRT lecture, we just say, oh, theta has some type of variance, but this is the multi-level version of that whole theta having variance.
Just a notation note, this thing at the end is what that term is for. Like, this is the E for the person level theta. That's why there's 7,000 subscripts in a row. There's
person within school for that theta.
Yeah.
Because guess what? There'll be another E coming up pretty soon, too. So question for you, how many random intercepts do we have for school? In this? 10, thank you. How many thetas per person do we have? Just one. So what we're saying is, this is the same across every item. All right, and so we don't see an item subscript here. Even though y is there, that y doesn't have a subscript I in the notation is is just as insane as
It's
the
the
model.
theta that goes with the y's.
That's
why.
right. It's the theta that goes with the y's, but there's no subscript there where there's subscript here. But anyway, this is 1 theta per item. So this is like a person's mathematics ability. But what we're saying in this model is there are differences in people, potentially differences in people in their math ability. And that, because we have a random intercept for school, there are potential differences in school on how easy or hard the item happens to be. All right, so each person, if you think about what's happening, each person gets a school. That means what the intercept per person will be different depending on which school they're in. Right? So it's like having an individual, different type of measurement model. If you go to school 1, here's how hard the items are. If you go to school 2, here's how hard the items are. Right? It's almost as if we have, in an IRT sense, differential item functioning across school. But we're okay with that. We're going to build that to measure the school itself. It's weird, but it's where it is. Any questions so far? Yes, please.
Struggling to understand where you put this, so that you said it has no slope because it's 1, and then, like from a multi-level perspective, this is a predictor of what? Of our math
Yeah,
answer for this item as a person in that school?
that's right. Yeah,
Okay.
that's right. We're going to say that we haven't observed a person's math ability, but how hard or easy the item is depends on which school they go to. That's it. So we're building toward where we need to go. This, if this were our final model, it actually I don't think would make much sense, right? Because now we have non-invariant items, right? We saw that there's variation across schools in the item parameters, right? But we're going to estimate a theta. So that theta will be more or less a different type of estimate depending on which school a person is going to. But this is a necessary setup to get to where we're headed. Right? As a final model, this doesn't make any sense, though. I don't think. Lisa, do you have anything to add?
There shouldn't be an I after the C's and the betas because I got 2 I's in there. That's wrong.
Right here?
Yeah, that I is away. And then the one on the top too. On the first model, I have it in the same thing.
Copy and paste.
Yep. Yeah, that I does.
There we go.
There you go.
But this is not ChatGPT making this, I promise. Okay, should we estimate this one? Estimation, the description of the estimation will go a bit faster this time. I will ask you to just go with what I told you before. We don't need any additional Cholesky factors or any of that stuff. But let's take a look at the model itself, because that's, again, where I like to start. This model line, we have, again, the loop across items and persons. Each observed item now follows a Bernoulli logit. We have a fixed intercept. Here's our item random intercept for school. And finally, we have our person theta. Right? That person theta is like what we had in IRT, in the IRT lecture like 3 weeks ago, it feels like, right? On Tuesday. The person theta is here. So it follows a normal distribution, mean of 0, and we estimate some standard deviation from the person theta. Again, it's a standard deviation in stan, even though the notation is some variance, which is the square otherwise. And so because we're estimating the person theta standard deviation here, we're using a log normal distribution as a prior, and now we need to input to stan data that would indicate the log normal theta standard deviation mean prior, and the prior hyperparameters for the standard deviation of the log normal. Questions? So it's not big differences in code here. The rest of it is literally the same. That's the mess for the item random intercepts covariance matrix. Again, we can output that down here. Here we have our calculation of the expected log posterior density. So that's used for LOO. And then, believe it or not, even though the model adds 1 theta per person, so we're adding 3,100 parameters per people, and 1 parameter for the standard deviation, we only have 2 more pieces of data we have to give Stan right now. Those prior values for the person's standard deviation mean and standard deviation. And because we only have 1 of those, it's just a single number for each, not a vector. Any questions? Okay. So the data, I'm using those values right there. Pretend it ran, because it did run. We take a look at convergence. Ooh, not as good convergence this time. Yeah, so this is what we're going to start seeing, right? Our convergence is going to start getting sketchy as we go forward. And yes, I probably could have tightened priors or otherwise tried to play around with this, but I actually did for a while, and I got to this, and I decided this was where it's going to stop. So otherwise, we may not have a workshop. So it's, that fear of, we got to do this in a couple weeks.
Well, I keep telling him, I think it's more fair for him to show you what actually happens than a textbook example where everything's neat and tidy and converged and easy, because that does not exist in real data. So this is a very realistic depiction of the fight to get to the end of the model.
Well, let's take a look at some of these. Do you want to see some of the parameters, the person thetas? Okay, let's do person theta first. How's that sound? These are our estimates of our people. You'll see, actually, these are mostly converged right here, right? And these are, again, on it's a continuous variable mean of 0 for our person estimates. But you can see this is indicating people above or below average. But remember, it's interesting. What average is here is sort of weird, because now each person from a different school is going to have a different set of parameters, a different type of item. Right? The item may be easier or harder. So it's not really a fair comparison, I don't think, across people from schools. Should we take a look at the standard deviation for that? I think that's what it is. There it is. Again, this is another converged parameter, 1.49. So you see there's a little bit of variation in theta, actually quite a bit of variation in theta. Here are the random intercept correlations for each. You'll see these are fairly similar in size to what we had before. So this is almost like what you were saying about between versus within, because we added the person's theta, and I didn't plot each of these, but I probably could have. The question would be, do these change a lot when we add person's theta versus not, right? Let's do the item random intercept standard deviation. And here are our standard deviations for the items as well. So you'll note all of the sets of parameters I showed you, most of them have converged values. So that 1.1 value, it may be up in that list of all those correlations. I'm not going to scroll through all those trying to find it, but and I could search it, but I don't care to do that. I think I searched it when I was going in, and I should have wrote it down. But here we have our item standard deviations. What else do you want? You want to see the gammas? See what those look like as well? And here are our gammas. Again, the same, just eyeballing it, approximately the same magnitude. Again, I see that the first 5 are negative, the last 5 are positive now. Yes. And now these are represent if you think about what this means, because we just added in the model. Let's talk about that just a bit, because it's a little bit weird. We're talking about this term right here, and I don't have the composite equation on here, but you have to remember this beta gets replaced by these terms. So it's these terms plus this theta that we have. So this item random intercept now represents the expected log odds of a correct response to that item for a person who's at the mean theta, who attends a school who is at the mean of the school random intercepts itself. So basically, we have to think about that intercept conditional on all of the other terms in the line being 0. And then when we convert, if we wanted to convert that intercept to a probability, that probability would be conditional on that person at theta of 0 with that school with the u of 0. How's it going? All right. I know it's starting to. We tried to build. I hope today justifies where we put all the slides from the last 3 days, because it's like we're pulling from every section of each day to do this, right? Whether it's Bayes or Stan or IRT or multi-level or the bad jokes. Yes.
So just to, if we now want to, for example, a measure for the reliability, I would assume it's a kind of a composite score on the between level side and kind of it's inflated.
So measures for reliability are difficult here because there's no one. What we would actually be getting into, now let's talk about what reliability would be. We have 2 things to be reliable upon, right? Theta or the u, right? So we want reliability for the person, or do we want reliability for the random intercept of the school?
11 things.
Quite a few things, right?
And I would assume that school is kind of inflated if you compare.
Well, let's take a look. Let's talk about theta first. Would that be okay? No, there it is. Okay. So in IRT, reliability, there's no one number for a reliability. Actually, in any generalized measurement model that's not normal, there's not one reliability. I know people will use that. But you mentioned before McDonald's omega. If you apply McDonald's omega here, what you're applying it to show is if we were to add up the scores. Well, what are we talking about adding up here? Are we adding up the person's score? Are we adding up the school score? Right? So we have these multiple levels of measurement. Instead, we much prefer talking about conditional standard errors of measurement. Right? And in IRT, the conditional standard error of measurement varies as a function of the test, as a function of where theta is located. But let's take a look. Here, somebody who is about 1 1.25 points below the mean, standard deviation is 1.49, so it's not a full standard deviation below the mean, has a condition. The second column right here is this is the posterior standard deviation, which is our Bayesian version of the conditional standard error of measurement. So what happens is we will have this be lower or higher depending on which point of theta is present. So here for a negative 1.24, about 7.2. As we get lower, it actually gets more variability, because here's a negative 1.37 as a mean, and that standard deviation is 0.745. And if we go the opposite direction, if we're close to 0, we're about 0.682. And then like a 2, which is positive 2, 0.784 again. So if we were to plot this, the size of the standard error of measurement would have this U-shaped curve. And we could plot the EAP estimate by the standard deviation. Would you like me to do that? I don't know if that would help. I probably could do that.
But it would like the test information curve.
That's right. It's the inverse of it. That's right.
Yeah.
Yeah.
And if you want to talk about that as reliability, it's information divided by information plus 1, puts it between a metric of 0 and 1 that normal people can understand.
In this case, it won't be plus 1 because we estimated the variance.
Oh, darn it.
So
Close.
the reliability part of it is interesting because if you're in the educational world and educational measurement world and using IRT, you don't ever say that word because you just want that number. But for the rest of the world, you do want reliability, and yes, you can convert it into it, but we didn't calculate it. There's other aggregation methods, so you can ask what's the average reliability we have in the assessment. Those always seem to fail because there's no good way of describing reliability without a graph for it. Does that help? Do you want to see any other information about this, or are you okay?
No, that's super cool.
Okay, gotcha, thank you. Other questions?
Do you want to take a break yet?
Would you like to take a break yet, or do you want to go one more? Ah, I see yes for a break. You've decided, and I'm on your side. All it takes is one. I'm just kidding. Is a break okay now? All right, I see more thumbs up. Get extra coffee. Do what you need to do to stay alert. That's 2 models down. We have 7 to go.